Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is to revisit two of the previous effects we created to add multi-channel support. They are the Beat Crusher, the first effect we created in this series, and the Oscilloscope, which is the first visualization effect that we created in this series. So let's jump right into Reaper. Let's create a track and add our Beat Crusher. Oh, before we do that, I definitely want to not hear, at least not for now. So I'm going to mute the master track as we usually do. Okay, so I'm going to add the Beat Crusher. And let's look at the code for the Beat Crusher. When we did this, we were young and naive, and we made some mistakes here. And one of which is we don't have support for multiple channels. We are only looking at the left channel, so we want to fix that. But there are some other mistakes as well. To visualize these mistakes, let's bring in the oscilloscope, which is the second effect we are going to change anyway. So I also want to have some sort of wave here, and I want to have control over the wave, so I will add a tone generator. And this is the one that comes with Reaper, and I keep promising this, that I will create my own. I think it will be the next effect in the series. The next one we are going to do is a tone generator. Anyway, enough with the promises. So we have here a tone generator generating this sine wave. We can look at the sine wave in the oscilloscope by zooming in, and we look at the shape, and it looks like a sine wave. The Beat Crusher is in the middle between the tone generator and the oscilloscope, so we can leave the oscilloscope open, come to the Beat Crusher and change the resolution or the number of bits, and you can see that beautiful shape coming together. Awesome. So by this point, if you have been watching the rest of this series, it should be kind of evident how to add multi-channel support for this effect. Instead of explicitly naming channels 0 and 1, we can loop over the channels. So we start with we start like that with channel -1. We loop over the number of channels and add 1 on every loop. Then here in this part, we take the sample on the particular channel and we apply the formula for the bit reduction with the sample on that channel. Then we save, and the effect here on the oscilloscope should be none at all, because the oscilloscope also only supports one channel. But we are going to add multi-channel support soon, and then we may be able to look at the distortion happening on different channels differently. So that's one problem. But I noticed another problem, and that has to do with the number of bits. So let's look at, for instance, at the number of bits equals to 2. If we have 2 bits, then we should be able to represent 4 values. Each bit can represent 2 values, 0 or 1, and we have 2 of them, so 2 times 2. And we should have 4 different values represented here. But you can see on the oscilloscope that we only have really 2 values, these 2. And yes, there are some flukes here, but I don't think we should regard them. We should just look at the 2 that we see here. And if I bring this to 3, then we should be able to represent 8 values. That's 2 times 2 times 2, because we have 3 bits. But we are not. We can zoom in and we can count 1, 2, 3, 4. It seems like our slider here is off by 1. And we can fix that by just adding 1. So we can come up with a slider section here, and that is because we want to change the number of bits. So we want to make an adjustment to the number of bits. So we want to do some computation here and here as well. And it's kind of annoying to have to do this part, the exponentiation, multiple times, even if, and especially now that we have multi-channel support, we're doing this computation a lot of times, but this is actually a constant. So I don't know what to call this. Maybe the bit reduction factor, and now the number of bits is off by 1. So when we had the number of bits equals to 2, it was reacting as if we had only 1 bit with only 2 values. And with the value here of 3, it's reacting as if we had only 2 bits, because it only allows us to represent 4 different values. So we actually want to add 1. So now that if the bits here is equal to 3, then we will have 4 here as the value, and that would be correct, I think. Anyway, we'll see. And then this bit reduction factor will come in here and there as well. So now we are saving that computation from happening multiple times. And of course, we can only do this because we learned about multi-channel, we learned about sliders, the slider section. So that's why we are able to do these changes now. So I saved this and I will play on the oscilloscope, and we definitely have more values happening here. I'll make the oscilloscope bigger here on the bottom of the screen, and then we can play with the values. So I'll come back here to number of bits equals to 1. That is correct. We only can represent 2 values with 1 bit. If the number of bits is equals to 2, then we should be able to represent 4 values. I will pause here. 1, 2, 3, 4. That is good. And if we have 3 bits, then we should be able to represent 8 values. And I'll pause this and count 1, 2, 3, 4, 5, 6, 7, 8. So now this is correct. And it also has multi-channel support. So that's all I want to do here with the bit crusher. Now let's move on to the oscilloscope and add multi-channel support on that as well. So I'll open here the code for the oscilloscope to add it. And this time it won't be as easy, almost trivial as it was for the bit crusher. We cannot only loop over the number of channels because we are storing a window of samples. We have this buffer of samples. And that buffer of samples is so that we can store the samples when they come in, and then we can plot the samples using that graph. The problem here is that we are only storing the samples for the first channel. But we can have multiple buffers, 1 per channel, and then we store the samples for all the channels. It's a similar trick to what we did in the previous video on this series, in which we added multi-channel support to RMS, and we had to store the samples, the raw samples. When looking at the definitional version of RMS, we had to store multiple buffers, 1 per channel. That's the same thing we are going to do here. So instead of having the samples just be 1 buffer, we are going to have multiple buffers. And we are going to do the same trick. So we'll have the available address. I'll just call this address now. It starts with 0, and anytime we want to allocate, we use address, and we add to address the number of slots that we are taking. And this is going to be, in this case, I want to have number of channels. So what we are going to have here in samples is a multidimensional array, so that we will be able here later to say something like samples at channel, something like that, and then index in the samples counter. So that's what we want to do eventually. So it starts by having the number of channels, because we are going to index here by channel. So at most samples we have the number of channels, and then we need to loop. So I'll start with channel equals -1, same trick as before, and we'll loop over the number of channels. And the first thing we want to do is to increment the channel, and then samples at channel will be address, and address now is well, actually the sample size, right? So that's what we want to do. So we want to move this up and probably want to keep this in one line so that, oh, actually the initialization of the address, I'll leave it, I'll separate it this way. So this paragraph of code is setting the number of samples. This paragraph of code is setting up the address. This free mbuff now needs to look at the address plus 1. That's the next index that is available, and that's how we communicate to Reaper that we have stopped using the big array of memory at that point. And here in the samples, we are initializing the samples on that channel with the address and adding the sample size to the address. So we will have now multiple buffers. And samples counter doesn't change, and old is paused equals paused. Yeah, that all remains the same. And we definitely want to run this code with the number of channels available to us, but I don't think it's available to us in the init block. So let's test this. And of course, at this point, the effect is broken, so I won't even look at the output. I won't even look at here because I know the thing is broken. I just added some new code here that changes the meaning of samples. I guess it may still work by accident, but I won't look at the output for now. So let's just test my assumption. I'll create here a variable called debug, and I will set it to the number of channels and save. I'll bring this down so we can look at it. The number of channels here is 0, and this track definitely has more than 0 channels. So I think that the problem here is that the init block doesn't have access to the number of channels. And I tried to look for the documentation about this, and I couldn't find anything that explicitly mentioned that this is the case. But I think that if we run this on the slider section, and we kind of already have a slider section here, so we can just, yeah, we may need to move things around. So instead of doing that, we already have a slider section, so I'll just move debug here. And now when we save this, it still doesn't show here. It's still showing the number of channels as 0, but we learned in the previous video on RMS that if we add a serialize section that is, it doesn't have to do anything at all. It can just be empty like this with a single dummy expression. But if we save this, then it should work, I think. Let's see. Yep, and it does work. Ooh, and you know what? If we have the serialized section, it seems like even the init section has access to the number of channels. So it appears, because I created a new variable like debug3, and I saved, and it still has debug3, still has the value 2 here. So that is fine. And I think it will still run if I hit play and pause. You can see the cursor here on the top. If I hit play and pause, debug3 still has that value. So it seems like this is working like it's supposed to. So the serialize hack does its thing. So we have the samples set as a multidimensional array, and we can move on to the rest of the code. So here in the slider section, I don't think I need to change anything, or maybe I do because I have some set here, and this is the number of samples. So I guess I should, instead of saying samples size, I should say address, right? Because we want to initialize the whole, all the buffers, not only the first one, but all the buffers we want to initialize to 0. So putting address here is kind of a hack, because if we had other variables here, other memory allocations, we would use address as well. So this is kind of a hack. So instead of doing this, I'll say sample size times the number of channels. And this way we are initializing the samples multidimensional array correctly. Or maybe we could do something even more meaningful. I guess it would be more meaningful to do it like that. So let's see. Let's see what this code looks like. So this is one expression, and that's another. So we are going to move that to another line. And I'll put some parentheses here because now I want to do multiple things. Actually, no, I don't want to do multiple things. So I'll leave this in one line for now. Let's see. But I want to loop over the number of channels. So I'll do a loop. Yeah, I will have multiple statements because I will do a loop similar to this one. I'm going to, in fact, copy this code. Move it here. So that I don't need to do this multiplication. Actually, it will be more meaningful if I do it this way. So this mem set is what I want to do here in the loop. And I'm looping over all the channels with the same setup as before. Now, on this mem set, I don't want to look at samples necessarily, but samples at channel. And I want to set the number 0 to samples size, which is the size of this array as we set it. So that is better. And of course, this kind of wastes a cycle or two because it's doing this loop, but I think it's more meaningful to write it like that. Now let's look at sample, which is collecting samples. So if it's not paused, then I will look at the samples counter. I will increment the samples counter and do the circular buffer thing. And then we actually want to loop over and look at all the channels. So I'm going to loop over using the same setup as this one. And I will do this line over here. And of course, I want to do this on the channel, and I want to look at the sample for that channel. And with that, we have collected the samples on the multiple buffers. Now we need to plot this. How do we plot this? Well, I would like to use colors to represent the different channels. Let's see what we have here. Oh boy. Okay, not bad. Continuing to zoom in. Yeah, so this is still working because it's only plotting the first channel, but the first channel is there, we are collecting it, so this still works. Perfect. In fact, I think I will decrease just to make this wave more recognizable. I would decrease the number of bits to 2. So with 2 bits, we should have 4 values, and we can look at the little steps on this ladder, and I kind of think it looks nice. Anyway, so I would like to use different colors to represent the different channels. And usually in some gear I have the left is represented with blue and the right is represented with red. But here in this implementation, I don't have necessarily only 2 channels. I may have 4 channels, 64 channels. Who knows? I may have more channels. So what I'm going to do is I will draw lines that go from blue to red. So from left to right, from blue to red. And left will be pure blue, right will be pure red, and in between we'll have shades in between. So I want to do this plotting, but first, actually, I will do some setup so we can look at the results when we have them. So we continue to have, the first thing I want to do is actually increase the number of channels on this track. So I'll have maybe 4 channels. And now I'll add a bunch of these tone generators. One for each channel. And I am going to set up the pins on the ins and outs of these effects so that on the first tone generator, we don't need any inputs and we are outputting to the left. The left output or the right, because they are the same, I will output that to the first channel. In fact, maybe if I copy and paste now, it will keep the pin assignment. Maybe, let's see. Yes, so the first tone generator outputs to the first channel, the second tone generator outputs to the second channel, the third tone generator outputs to the third channel, and the fourth tone generator outputs to the fourth channel. like so. Also, they output different frequencies. So this is going to output, the first one is going to output an A, the second is going to output a B, the third is going to output a C sharp, and the fourth is going to output a D sharp. And they are one step apart. And now we have multiple channels coming into the bit crusher, and the bit crusher now has this assignment that it's bit crushing all the channels because we have implemented that just now. And the oscilloscope also should have access to all the channels, and it does. So now the oscilloscope is storing all the channels correctly, and when we implement the thing, we will be able to see the different channels being plotted. Now let's go over this code, and this part is just defining a variable that is the middle in the horizontal axis. This is drawing that faint white line that represents 0. We're going to keep that white. And then this is setting the color of the line that is representing one channel. And it's setting that to white because colors are represented between 0 and 1 in JS effects, and 1 is white, 0 is black. And then this is actually doing the plotting. So what we are going to do here is we are going to loop over all the channels, but this time we don't want to use the channel variable because this part of the code already uses the channel variable, and this part of the code runs in parallel. So they may be running at the same time, and then they would be using the same variable and stepping on each other's toes. So instead of using channel, we are going to use GFX channel here, and we don't need this part. And then in here, we are going to do this whole block. So we are going to do this whole block multiple times, one per channel. Oh, you know what? In fact, I don't want to go over channels from left to right, because when drawing, anything you draw is on top of everything that was already on the canvas. And I want the thing that if you have multiple channels overlapping, I want the left channels or the first channels to appear on top. So if you have both left and right with exactly the same signal, so maybe your signal is mono, then I want the line to appear as blue, the left channel, not red, the right channel. So I will loop over the channels in reverse. So I'll start with number of channels minus 1, and I'll loop over the number of channels. That stays the same, of course, but then I will subtract 1. So now I'm doing the loop in reverse. It's a similar setup, but in reverse. And then we need to select the color, and we are only passing one argument, and that is the same argument for red, blue, and green, but in this case, we want to have different colors. So I'll add here the red, green, and blue. So when we are on the left, I want the thing to be completely blue. So that means I want to have 1 here and 0 here. So that's what happens when we are on the left, which means GFX channel is equal to 0. So I will multiply by 1 minus GFX, or actually number of channels, minus the current channel, and I will divide this by the number of channels. What's going on here? Well, I want a multiplier for 1. I want a multiplier. Actually, multiplying by 1 is meaningless, so I can do just this. So what I want is a number between 0 and 1, such that when the GFX channel is 0, then this number will be 1. And when GFX is the number of channels minus 1, then this number will be 0. Because when I am on the right, I should see no blue at all. And GFX channel starts with number of channels minus 1. So I will take here the number of channels, and well, actually it should be number of channels minus 1. and it should be number of channels minus 1 here as well. So that's my maximum value. And I'll subtract the current value, and then I will divide by my range. So this is guaranteed, this part is guaranteed to be between 0 and number of channels minus 1. And this is number of channels minus 1. So this whole number is guaranteed to be between 0 and 1. And I'll have a similar trick here for the red, except that instead of doing this, I'll do just that. And now this number is also between 0 and number of channels minus 1. And this part here is number of channels minus 1. So this whole number is between 0 and 1, such that when we are 0, then g of x here is 0. This whole thing will be 0, and we'll have no red when we are on the left channel. Oh, and you know what I just realized? The first thing I do here on the setup is to subtract 1. So I should start on the number of channels. And of course, I don't have samples at I don't have samples at number of channels. That is not defined. The thing that is defined is number of channels minus 1. That is the maximum index we have on the samples. But because we are initializing here with the number of channels and then we subtract 1, we start with this one. So that is the right way to do it. And now I think the rest of the setup is correct. But I guess it may be clearer if we write something like this, color factor. And the color factor is this calculation. I don't think there is any better way to do this. So the color factor is this, and then that part may be easier to write if we just say 1 minus the color factor. So this number is more easily seen as between 0 and 1, because that is our current channel, and that is the maximum we have for g of x. It starts with number of channels minus 1. So it starts with 1. And then here we'll have 1 and 1 minus that. Okay, so I guess this is a better way of writing this. And then we'll do the samples counter, which is this whole setup to do the loop. And here we have the loop itself. So I guess the setting of the color, it should be here before the loop that actually does the drawing. But in the loop, we don't want to look at the samples. We want to look at the samples in the current channel. And let's save that, and let's look at the oscilloscope. And we have colors. Let's see what's going on there. So we have a bunch of waves here because we have 4 channels. This has a bunch of waves. So what if instead we just have 2 channels to begin with, or maybe just 1 channel to begin with? So if I play now, I see only 1 channel and it is blue. There's something weird here that there is a red line, and I guess that is because the number of channels is still 4. Yeah, the number of channels is still 4. There are 4 channels. I can see here that the variable that loops over channels is equal to 3. So from 0 to 3, we have 4 channels. So the channels from 2 to 4 are muted, and that's why we see the red here in the middle, because it's 0. And also that's why we see some squiggly here on the right, because it's trying to draw some weird shapes here. But now we can add another channel, and yeah, it's already plotting. Let's pause this. And now there is a different color. It's not exactly blue. It's in the middle between blue and red. And there is red here in the middle. I will zoom in so we can have a better grasp of what's going on. And yeah, we have the blue, the left channel, and this kind of purple-ish. That's the second channel. What if instead of having the second, we have the fourth? Then we should see 2 waves, 1 blue, 1 red. Let's play. And yeah, that's what we see. So let's pause. 1 blue and 1 red. And I can, I guess, zoom in to take a better look. Yeah, and they are. And the bit crusher is also doing its work, by the way. So it seems like everything is working today. Awesome. Now let's put in all the channels, and we should have this kind of colorful and beautiful effect. It goes from blue to red, and there are 2 shades of purple in the middle. I'm not sure I'm too happy with the colors though. They kind of look bad against a dark background, so I wonder if I should have a white background instead. So let's try that and see what it looks like. I have here the documentation for GFX, and it seems like there is this variable that clears the frame buffer to a particular color. So I'll set this variable here, GFX clear, and I don't need this part, so I'll close it for now. And I need to set this to a packed RGB that looks like this. And then I'll set red, green, and blue between 0 and 255. So when I save this, now the frame buffer clears to white. And I'll zoom these wave shapes a little and pause. And yeah, I think it looks better with a white background. So that's what I'm going to do. I'll leave this background white. And now this is working. It's doing multi-channel oscilloscoping. Awesome. I just used oscilloscope as a verb. I don't think it's a verb. Anyway, so yeah, I tested with 4 channels. It's all working. There is one more thing I want to do before I leave this, though I think this is looking pretty good. And that is, I know I changed this in previous episodes several times, but I don't like this variable. I don't think it reads nice. I don't like the way this reads. So I'm going to instead do something else. And this is, the slider is going to be the play state. Oh, actually, this is a set variable by Reaper, it seems, because it turned red. So play state. Yeah, that variable is special. So no, I will say that this is the state. There you go. And here in the init section, we will have the old state is equal to state. And the same here. And I'll change this throughout, but the idea here is I'll have a state that is either 0 or 1, but then here in the initialize section, we'll have the state play is equal to 0 and the state pause is equal to 1, because that's how they map, right? Play is 0 and pause is 1. So I'll have that. And whenever I'm interested in, for instance, this, if not paused, that doesn't read nice. So I can say if state is equal to state play, then collect samples. And here I'll do something similar. So slider old is paused, it turns into old state equals to state play, and the state, actually it's the other way around. This is pause. So if the old state is paused and the current state is play, then I will reset the buffers to zeros. And I think that about does it, really. Yeah, let's save this and try this out. I'll do a full compile reset as well. Full compile reset. I can zoom in. Zooming way in. I can pause. That does the right thing. I can move horizontally. I haven't done that in a while. I can move horizontally. I can zoom vertically. I can zoom in and out horizontally. And then when you know what? I'm going to leave this as paused. I'll zoom out and we'll see when I hit play. Yeah, it starts filling in the buffers. But for a moment there, it was completely empty. The buffers were empty. So the emptying out that happens here on the slider section is doing its job right. And there you go. We have an oscilloscope that is multi-channel. Okay. I said I would leave this with just one more thing, but I guess I want to do yet another thing. And that is this move versically factor. I don't like how I have to use this every time I am using the middle. I kind of have to use the move versically factor as well. So what if instead, since we extracted this variable, what if we used the move versically factor in the middle here? And we can do that. So we'll do a bunch of changes here to make this happen. So currently what I have is this, and I'm going to embed this idea of subtracting the move versically factor in there. So I'm going to start with this, and then we can, of course, take this out. And then we can realize that this factor is appearing here and there. So we can actually extract this, factor it out, and then we end up with something like this. Okay. And now we need to change everywhere where we are using this middle. We need to, I forgot to multiply. Yeah. So this is the actual middle, and this is the adjustment with the factor. So now we can change anywhere we are using this to, and that we are doing the adjustment. We don't need to do the adjustment anymore. So I guess that happens there, and it happens here. Now this looks a lot better. We are drawing a line from 0 to the whole width on exactly the middle that has already been adjusted to the move versically factor. I'll save this and we'll check when I have... I'm drawing this line in white. I should probably be drawing it in black. So instead of... it's actually being drawn in gray. Let's see if this shows up correctly. So I'll pause, I will zoom in a whole lot. And yes, we do have a gray line here in the middle. So that is kind of working. Now let's move horizontally this line. Not move horizontally, move vertically. And the line is going up, and the line is, the gray line is going down. Forget every other line because I haven't changed that part yet. That's why it's all messed up. But the gray line is doing the correct thing and moving up and down. So let's continue. The gray line is being moved up and down. Let's continue to look for all other uses of this. So what I just did here is I selected the variable by double clicking and I hit Ctrl F, and then it starts to find a string with the string that is selected. So I just hit return and I can hit Ctrl or Command G and go to the next occurrences. So now here we are doing the same deal. We are doing that adjustment. We don't want to do it. But we have yet another occurrence of the thing here, and that is not doing the adjustment for the move vertically factor. So what I actually want here is to have some notion of amplitude. So I'll have amplitude is equal to this. And I guess I could kind of refactor this by putting the amplitude here and using amplitude there. But I don't actually want to do this because I think that they are two different notions, the notion of middle and the notion of amplitude. And I'll probably call this the amplitude height. And then this is amplitude height. So now we go to the middle, we subtract the sample times the amplitude height times the amplitude multiplication factor. Let's save that, and then coming back here, I'll do a full compile reset just because I don't know. I think it's a good measure. So I'll pause, zoom away in, and we see a gray line in the middle. We see all the 4 channels with different shades, and then we can move horizontally and we can move vertically, and all the shapes are being moved. And we extracted the variable, we extracted the notion of moving vertically in a way that I think makes a lot more sense. And we can move horizontally all the way up so that the gray line lines up with the top of the view, all the way down so the gray line lines up with the bottom of the view, and all the other lines are moving along with it. And we also extracted the notion of the height of the amplitude, which I think is a nice thing to do. And that's all I have for you today. Thanks for watching this video. Make sure you subscribe to the channel if you are interested in these kinds of things with programming and Reaper and all sorts of programming, really. I'll have other things coming up in the channel soon. Thanks for watching. I see you on the next one. Bye.